We want to take a couple minutes and look at some review items for your test on Friday. It'll be good that you watch this video to give you a couple of helpful tips to do well. Okay. The functions that I'm going to use today on this practice are going to be similar to the ones I used Friday, so it won't be much different. If you want some more practice, it'll be we'll do a ton on Thursday, a ton on Tuesday. Wednesday we have a benchmark exam. So these are the 6 items that will be on the test, guaranteed. Okay, you're going to add and subtract and multiply polynomials. We'll do that last on a separate paper. Okay. We're going to take polynomials, and all of them will be in factored form already, unless it's simple things like identifying polynomials by their degree and number of terms. So the largest power, and then how many terms there in there. Tell the end behavior of the polynomial based on the largest power and its coefficient in front, the number in front. You're going to tell me the polynomial will be in factored form already. Okay, you don't have to factor them, but you'll tell me where the roots are and if they cross or touch at that place based on its multiplicity, which we've talked about several times. You're going to tell me how many turning points there will be, and if those turning points are global maximums, global minimums, local maximum, or local minimums. Okay. And the last thing we'll do is factor simple trinomials as well as perfect square and perfect cube, difference of squares, and sum of cubes, difference of cubes, binomials, like we did last week. All right, so let's just get started with a simple one like number 4, 5, number 4 and 5. Okay. Oh, and you know what? Number 3 as well. 3, 4, and 5. All right, so let's just take a function that's factored already. Let's say x plus 1 squared, x minus 1, x minus 2. Okay, so this is a polynomial that's factored. It's got 1, 2, 3 pieces factored already, but you recognize first off that right there tells you something. That's called a multiplicity, and that's going to tell you at this particular factor's 0, that's going to touch because it's even. Okay. These other guys, they have a multiplicity of 1 and 1, so they're going to cross at those particular zeros. So our very first thing that we did with these, back when we did these like 2 weeks in a row, we took the factors and we set them equal to 0. Read the instructions, okay? We're going to do all 3 of these things. We're going to tell the end behavior, we're going to tell where the roots are, and if they cross or touch there, we're going to determine how many turning points and whether they're global maximums or minimums. We're even going to draw a rough graph right here in the bottom. Okay, so the very first thing is set the factors equal to 0. So when they're set equal to 0, we get x plus 1 is equal to 0, so that means x is equal to negative 1. That means that we are going to be crossing the x-axis there. Solve it for x here. We're going to cross the x-axis there, and we're going to cross the x-axis there. So let's mark that on our graph. Okay. So at negative 1, there. At 1, right here. And at 2, right here. Okay. Now, like we said before, we're going to cross or touch at particular places based on the original multiplicity of those factors. So at negative 1, x plus 1 was the factor. Okay, its multiplicity was 2, which means it's even, so it's touching there. So we're going to put a T under that for touching. We're going to put a C and a C under these for crossing. Their multiplicity is 1 and 1. Odd, so they're going to cross there. Okay, so at negative 1 right here, we're going to touch and go away, or maybe we're going to come up, touch, and go down. But we're touching here, we're not going to cross across the x-axis because of that situation. That's the way it always is, whether it's 2, 4, 6, 8, 10. As long as it's even, we're touching. If it's odd, we're going to cross the x-axis. Okay. End behavior. Okay. Tell the end behavior of the polynomial. The end behavior is based upon the largest power of x, and that isn't not represented by the multiplicity. It's represented by how many x values we have listed here. So we have 1, 2, 3, 4. So this is going to behave like x to the 4th. It's a positive in front, so it's going to behave like positive x to the 4th. We counted this one twice because of the multiplicity. It really makes a difference. So that multiplicity gets counted twice. All of these get counted once because the multiplicity is 1. If it was 3, we'd count it 3 times, and we'll have an example like that here in a minute. Okay, so x to the 4th behaves just like x squared or x to the 6th. All the evens behave the same. So it'll be up on the left side, and it'll be up on the right side. They're going to go in the same direction, and it's positive, so they'll both be going up. If it was negative x to the 4th, they'd both be going down together. If it was odd, they'd be opposite of each other. One would be down, one would be up. So there's that. So here are your zeros, okay, marked on the graph, negative 1, 1, and 2. We're going up on the left side. We're going up on the right side. And in between, what happens in between, we'll kind of draw a rough graph of what happens right now. Okay, so if we're touching, let's get that green back out. If we're touching at negative 1, as this guy comes down, it's going to hit negative 1, it's going to come back up because it's not going to cross through, it's going to touch and go away. And at some point it's going to come up and come back down, and it's going to cross through 1, and it's going to cross through 2. So it's going to come back down and cross through 1, it's going to come back up and cross through 2, and then it's going to continue forever in that direction. So it's up on the left, up on the right, touching, crossing, and crossing, and that's generally what the graph looks like. So finally, let's discuss about these turning points and these global max or mins, or maybe local max or mins. Okay, so obviously we've got a power of 4. Okay, that's the degree of the polynomial. So we're going to have 3 turning points. That's generally the rule. 1 less than the power. Okay, so we've got 1 turning point right there. There's a hump, a bottom part. There's 1 turning point right here as the top part, and there's a bottom turning point right there. So there's 3. Okay. Obviously the top of the roller coaster, that's going to be a maximum value. The bottom down here, that's going to be a minimum value down here. And this is going to be a minimum here because it's the bottom part of a hill. Okay, now it's just a matter of whether they're global or local. Well, this maximum is going to be local because it is not the largest maximum value in the function. The entire function goes up forever in both directions, so that is just locally a maximum value. Minimum values, one of them is global because one of them is the lowest point of all the graphs. So the lowest point of all the graph is clearly here. This guy is not going to go as low as that one goes. This is the global minimum value of the entire function. This is the lowest point on the whole function. There can only be one global minimum or one global maximum. And there is one global minimum right there. This guy will be a local minimum. Out of the surrounding area, this is the smallest point. But it's not the smallest point on the whole graph. So there you have it. Okay, we've done all the things throughout this whole thing. Okay, so let me kind of highlight a few things here. Okay, number 1, tell where the roots are. Well, we take the factors, we set them equal to 0, we tell where the roots are. Number 2, will it cross or touch at that root? Well, based on the multiplicity, we are touching there, we're crossing there, and we're crossing there, and we mark that on the graph. Okay? Tell what the end behavior is. All right, so we look at the largest power, we say, okay, it's even, they're going to go together, it's positive, so they're both going up. How many turning points will we have? Well, we're going to have 3 because the largest power is 4. We can kind of draw a rough graph. We're going up on the left, we're going up on the right. We've got zeros there, there, and there. So we're going to touch, cross, cross. 3 turning points, 1 local minimum, 1 local maximum, and 1 global minimum. All the turning points need to be labeled with minimums and maximums. Okay? And that's how we do that. All right. Let's do one more for clarity. Okay? Let's do g of x is equal to x times x plus 2 squared times x minus 1 to the 3rd. All right. Let's find the zeros. You take the factors, x, x plus 2, and x minus 1. You set them equal to 0. You solve for x. Well, x is solved right there. There's one of your zeros. There's another one of your zeros when you solve for x. And there's another one of your zeros. Now down here on my graph that I'll have on your test on Friday. Doesn't have to be pretty, but just kind of getting this done. Okay, I'm going to mark these for you. Okay, 0 is a solution. -2 is a solution. And 1 is a solution. Okay. Do they cross or touch? Multiplicity. Okay, what is the multiplicity of this particular factor? It's 1. That's odd. It's going to cross. -2. -2 has a multiplicity of 2. That's even. It's going to touch. Not just because 2 is even, the solution. Okay, I'm talking about the multiplicity of the factor. Okay, I don't care what this number is in here. I'm talking about the multiplicity. Okay. For 1, its factor is x minus 1, and its multiplicity is 3. That's odd. We're crossing. Okay, are we clear on that? Okay, so we are crossing, touching, crossing. We'll save that for just a minute. Okay, now as far as end behavior goes, okay, end behavior, how many zeros, what is this going to behave like? How many x values do we have? We've got 1 right here. We've got 2 right here because of the multiplicity, right? 1, 2. And then we've got 3 right here, right? Multiplicity is 3. So 1, 2, 3, 4, 5, 6. Okay, you can even just count the multiplicity and say that. 1, 2, 3, 4, 5, 6. So this is going to behave like x to the 6th, and it's positive out front. This is even, all right? So they're both together. So they're either both up or they're both down. The number in front is positive, so they're both up. Up on the left side, up on the right side. Just happened to be the case this time also. We're up on the left side, up on the right side. And notice when we were taking this quiz that you would get the end behavior right, and then you would get the crossing or touching wrong. And so when you would try to draw your graph, you'd come down here and you'd cross, and you'd come up here and you'd cross, and you'd come over here and you'd cross, and you'd end up going in this direction at the end, downwards, and you knew you needed to go upwards, and so you just come up here and draw through that line again, and that creates another 0. Okay, and that's a problem because we only had 3, and you want to make a 4th because you're not doing the crossing or touching correctly. Okay, so everything should match up perfectly with what you're saying here, and it does. So as we draw this, we come down this way, and at -2 we are touching. Okay, so I'm going to come down here, I'm going to touch, I'm going to go away. Crossing at 0, and I'm crossing at 1. So I'm coming up, and I'm crossing it again, and I'm crossing again, and going back up. All right, so now we have a local minimum, a local maximum, and a global minimum. Okay? Similar to the one before, but slightly different. Hopefully this helps clear up some things like that. Okay. Let's do one more just for clarity also. Okay, let's do pen. H of x equals x squared, x plus 2. Okay, so I'm going to do this quick. If you need to pause it, hit spacebar. So our factors are x and x plus 2. Set them equal to 0. That one's equal to 0 already. There's that one. Okay, now on my graph, okay, on my graph I'm going to mark those 0, -2. Okay. My end behavior, we're going to have 2 x's there, we're going to have 1 x there. So this is going to behave like positive x to the third. Positive x to the third is something that we need to remember how it looks, like a little snake going down this way, coming up, and going up that way. Okay, x to the third, x to the fifth, x to the seventh, all the odd ones, they behave the same when they're positive, and then they flip upside down if they were negative. Okay, so it would be up on the left, down on the right if it was negative. But this one's positive, so this is down on the left, up on the right. Okay, so on the left side we're going down, and on the right side of everything we're going up. All right. So end behavior is going to be like that. Now multiplicity, right? We've got 1, 2, right, for this one, so we're touching there. This has got a multiplicity of 1, so we're crossing at -2. We're crossing at -2, and we're touching at 0. Pay attention to that. We're crossing at -2, and we're touching at 0. All right, so let's draw this in. We're coming up from the left. We're coming up the roller coaster. At -2, we cross. So we cross, and eventually we come back down. We hit 0, and we're touching a 0, so we're going to touch and go away. Right, and it coincides perfectly with what we said about the end behavior. So everything crosses, it touches, and the end behavior matches, and everything's good. No more zeros that we're not touching the x-axis again anywhere else. Okay, so look, we've got a hump right there, and we've got a hump right there. Right, so that looks like a maximum value, and this one is a bottom of a hill, so that's a minimum value. So are they global or local? Global would say that the entire function, that is the tallest point, and clearly this goes up forever. This is not going to be the tallest point of everything. It's just the tallest point in this general area. So this is a local maximum. Same thing for the minimum. It's not the lowest point of the whole graph. There's the arrow that goes down forever. So this is a local minimum there. Okay. And as you know, we have a power. The largest power is 3. The degree of this function is 3. So therefore, we should have 2 turning points, and we do. We have 2 local minimums or local maximums or values there. Okay. So that is taken care of. There's the rough graph. We've got our zeros, end behavior, touching or going away, and max or min values. Okay? On our list again. Okay, so we tell the end behavior. Chuck that away. Okay? Tell where the roots and zeros or solutions are from a factored polynomial, if it crosses or touches at the roots based on the multiplicity. And 5, determine the turning points, whether they're global or local max or mins. Okay? Number 2, identify polynomials by their degree and number of terms. Okay, that's a simple one. So for number 2, it was simple things like I said, 6x to the third minus x to the third. Well, those are like terms. Okay, this is not a binomial because they have 2 pieces. These are like terms, so you can simplify this to 5x to the third, and this is a cubic, because the largest power is 3, a cubic monomial. Largest power is 3, so that's a cubic function, and it's 1 part, so it's just a monomial. Okay, another one like this maybe would be, let's say 3 plus 12x to the fourth. Well, first of all, that's not in standard form. Standard form would be largest power first, and then on down. These are not like terms, so they can't be combined. So there's 2 parts here. So this is a binomial. Well, what kind of binomial? The largest power is 4, which is a quartic. A quartic binomial. Okay, so things like that. 3 pieces would be a trinomial. 4 pieces would be just a polynomial of whatever degree that you need. Okay. Number 1, add, subtract, multiply polynomials. So I've got a couple of them set up over here. We're going to add, subtract, we're going to multiply these. So let's work on these real quick. These are really, really simple. You just combine the like terms. When you're adding the functions, you really don't need the parentheses because nothing's changing. You're just combining the terms that are alike. And the like terms, this is not multiplication. Do not get this confused. Pay attention to the signs. We're adding here. On this one, we're subtracting here. For multiplication, they're just smashed together. Multiplication. So now we FOIL. Okay? So pay attention to the signs. We're just combining the like terms based on the largest power. Based on the power, we combine the terms with the similar power. So x to the third is our largest power. There is no other x to the third. So we just write x to the third. Okay? Because that's combined. So we can scratch that one out. X to the power 2, we have a negative 8x to the power 2. We have a negative x to the power 2. We have a 19x to the power 2. We're going to add those together. Negative 8 minus 1 is negative 9. Negative 9 plus 19 is 10. So we have positive 10x to the power 2. We can scratch those out. We're done with x to the power 2. What are we going to add together next? The x's. 7 7x. We have a negative 7x. Looks like when they add those together, it creates 0x. We're not going to write 0x. We're just going to write nothing. And lastly, the number. 64 plus 3 is 67. 67 minus 2 is 65. All of these functions combine together to create a trinomial, a cubic trinomial, x to the third plus 10x squared plus 65. Subtraction is quite similar. You're going to do 3x to the fifth minus 9 minus this one. Okay, so that means we have to distribute that negative in here, which changes the signs. So instead of plus 11, we're going to do minus 11. Plus 13 becomes negative 13x squared plus x to the fourth instead of minus. The negative changes the signs, so subtraction does that. Okay. Combining like terms, now that we have the signs fixed, okay, the largest power looks like 5, so we're going to do 3x to the fifth. Scratch that one out. The fourth powers looks like it's positive 1 minus 1, so it looks like they cancel each other out by subtraction, creating 0x to the fourth, which I won't write down. There's no x to the third. Here's x to the power 2, so we have negative 13x to the power 2 minus 10x to the power 2. So combine those terms. Negative 13 minus 10 creates negative 23x to the power 2. And then lastly, the numbers creates negative 20. So we have a polynomial of degree 5, a trinomial, degree 5, subtraction. Okay, multiplication takes a little bit extra space. Okay, so we're going to erase some of this old stuff. We're going to move some of this other stuff out of the way. There we go. Now, what this requires is a little bit of foiling. So we're going to take 4x squared, we're going to multiply it by everything inside this one. 4x squared times 3x squared is 12x to the fourth. In fact, I'm going to have to write that over here. Leave myself some space. 4x squared times 2x is 8x to the third. I encourage you to pause the video and try this yourself to see if you can get this right. Follow along. 4x squared times negative 1 is negative 4x squared. I'm going to change colors to help you out. 3x is now being multiplied by everything inside. It's just like foiling. Okay, so 3x times 3x squared is positive 9x to the third. 3x times 2x is positive 6x squared. And then 3x times negative 1 is negative 3x. Lastly, 2 gets multiplied by everything inside the other parenthesis. So 2 times 3x squared is positive 6x squared. 2 times 2x is positive 4x. 2 times negative 1 is negative 2. We combine like terms finally. Looking for the largest power is 4, so our first term is 12x to the fourth. Scratch that one out. Our next term will be to the third power, so I'm going to highlight those. So we have 8, positive 8, and positive 9. Combining those terms gives me positive 17x to the third. We do not multiply those now. We're just simply adding or subtracting, combining the like terms. Power 2 is next, so we have negative 4 plus 6 plus 6. So negative 4 plus 6 is positive 2. Positive 2 plus 6 is positive 8x to the power 2. Scratch those out. The x's are next. Negative 3 plus 4 is positive 1x. And then we have the negative 2 all by itself. So there's our final answer. Those two guys being multiplied together foils out, combine like terms to create this 1, 2, 3, 4, 5, a 5-term polynomial of degree 4. So this is a quartic polynomial with 5 terms in it. Okay. That should be this addition, subtraction, multiplication. That should be some of the simplest stuff that we've done. Our last thing that we want to talk about on this video is number 6. Factor simple trinomials as well as perfect square or perfect cube binomials. Factor simple trinomials, okay? Let me give you a couple of examples. Okay. Give me another example. So simple trinomials like this, and also perfect binomials, the ones that we had like a perfect square, where we had problems like that, perfect cubes, problems like this, and problems like a difference of perfect squares, a difference of perfect cubes, and a sum of perfect cubes, maybe like 27x to the third plus, let's say, 216, okay? So these first, factoring simple trinomials, okay? So we need two values that multiply to be 9 and add to be 6. Obviously, 3 and 3 multiply to be 9. 3 and 3 also add to be 6. So x plus 3 times x plus 3 would be the exact way that you would factor this. And it could even shrink down to x plus 3 squared because it's something multiplied by itself. So that would be the proper factorization for a trinomial like that. X squared minus 3x minus 40, we would need it to factor. We need two numbers that multiply to be negative 40 but add to be negative 3. Okay. If you recognize, just pause this to see if you can get this right, because it should FOIL itself back out to be exactly what you have written here. Some factors of 40 would be, let's see, obviously 1 and 40, but if you add those, you never get negative 3. 2 and 20, right? 4 and 10, right? 5 and 8, okay? But if you recognize, if you said 2 or 20, one of them has to be negative, right? 2 or 20, if that was negative, they would never add to be negative 3. 4 and 10, they have a difference of 6, so that would not add to be negative 3. 5 and 8 are the ones that you probably want, because if you subtract 8 and 5, you get 3 or maybe negative 3, depending on the order that you have them. Okay, so this sign right here, when you're multiplying and creating a negative, one of them has to be positive and the other has to be negative to create a negative when you're multiplying. Okay, and because it's negative 3, the largest value will be negative, so it'll be positive 5 and negative 8, and when this FOILs back out and combined like terms again, you'd end up with this trinomial here, x squared minus 3x minus 40. So this is the proper factorization for that trinomial. So now we know what the factors are, we know where the zeros are, and everything like that, okay? So we had a lot of practice like that last Monday on the 30th before we practiced these. So this is a perfect square, difference of perfect squares, okay? Difference of perfect squares, which is when we have something squared minus something else squared, it factors into that, right? So what's being squared right here? 2x is being squared. 6 is being squared right there. Okay? So this will factor to 2x plus 6, 2x minus 6. All right? It's very simple. You just use the cheat code right there to help you out. Okay? As far as these guys go, this is a difference of perfect cubes. We talked about this all week last week. Still didn't quite get it, but a to the third minus b to the third factors to a minus b times a squared plus ab plus b squared. All right, so what is a, what is b, so we know where these puzzle pieces go. So 8x to the third, that is 2x being cubed. 2 times 2 times 2 is 8. It's a perfect cube. 4 times 4 times 4 is 64. So 4 is being cubed. So now we know a is 2x and b is 4. So those go right in the spots where a and b are. So this factors to a minus b times a squared. A is 2x, so if I'm going to square that, 2 squared and x squared creates 4x squared. So that's a squared plus ab, a times b, 2x times 4, that's 8x, plus b squared. B is 4. Take 4 and square it, creates 16. So this is the proper factorization. If it was FOILed out, it would create 8x to the third minus 64. Difference of perfect cubes. This guy down here is a sum of perfect cubes. What's being cubed right here? What's being cubed right here? We'll talk about that in a second. But the sum of perfect cubes, sum of perfect cubes, is when we have a to the third plus b to the third. How is that different than a to the third minus b to the third? It's not really different. The signs are just slightly different. A plus b is in the first group. I'll erase this right here. A squared minus ab plus b squared. Okay? Highlight the difference. Highlight the difference between the rules. A squared minus b squared. A to the third minus b to the third. Notice that it's a minus b to start and then pluses the rest of the way when it's minus. A to the third plus b to the third. It's a plus b and then a squared minus ab plus b squared. You figure out what the puzzle pieces are, you put them right in, just like Legos. So to finish this up, what is being cubed right here to create 27x to the third? 3x is being cubed. 3 times 3 times 3 is 27, and then x times x times x is x to the third. What's being cubed here to create 216? You can guess and check, but it's 6. 6 times 6 times 6 is 216. So now we know that the a value for our situation is 3x, and our b value is 6. We're going to have tons of practice of this. Hopefully you finally pick this up. So your final factorization for this guy should be a, follow the rule. This is sum of perfect cubes. So our first piece is a plus b. So a plus b, a squared, 3x squared is 9x squared, minus ab. So minus a times b, 3x times 6 is 18x, plus b squared, plus b squared. B is 6. 6 squared is 36. There is your final factorization of that sum of perfect cubes. Okay. That wraps up the review video. Hopefully this helps you. Take a lot of the practice that you get from me on Tuesday and Thursday, and take advantage of the opportunity to do very well in this last test.